Welcome back to Principles of Engineering. Today we're talking about some statics topics. And the first one we're going to talk about here is the idea of cross-sectional moment of inertia. And that's really how the geometry of an object impacts its structural rigidity. So let's get moving. First, you'll find some guided notes up in the module. If you download those will help you follow along in the computations that we go through in this presentation. And it has most of the graphics also in, so it'll make your note-taking a little easier because you won't have to draw so many pictures to understand the concept. So I'll pause for a moment while you download those. Let's get rolling. So when we talk about a structural member, or we talk about a beam that's being placed under load with a force, we talk about the moment of inertia. Now, this isn't the moment of inertia that we talk about or you commonly attribute in a lot of sports and a lot of activities in your daily lives. This is a statics moment of inertia, or the cross-sectional moment of inertia. And what this gives you is basically a property of the cross-section of the object that tells us how that object or that member will react when I distribute a force across it. So the key giveaway here is we're ever talking about moment of inertia and you see the measurement in a linear dimension to the fourth power. Example that we're going to use a lot in here are inches to the fourth power, or centimeters to the fourth power, or meters to the fourth power. That's a dead giveaway that we're talking about the cross-sectional moment of inertia. And really what it does is it's a way for us to equate the stiffness of an object that is related to its shape or its geometry. Now we learned a little bit about geometry of an object by finding the centroid of it. In this instance, what we're looking at is how the geometry affects the rigidity of the object. Now the general term here is the higher the moment of inertia term is, the stiffer the object is, given it's made out of the same material. So if I compare two objects and one has a cross-sectional moment of inertia, or I, of 10 inches to the fourth power, and the other has a moment of inertia, or I, of 20 inches to the fourth power, the one with the 20 inches to the fourth power is twice as stiff as the one with the 10 inches to the fourth power. So let's talk about this for a second. We look at two objects, and the first big picture thing that we got to remember here is joist versus plank. So when we talk about a beam in a joist configuration, we're putting it so that the tall side is standing up. The load is coming down on this yellow arrow in each of these two instances. So joist, the tall portion of the beam is sticking up. Plank, the tall portion is horizontal. And if we look at the same two beams, A and B, dimensionally they're the same, material-wise they're the same. All that's changed is orientation. So when I go to compute my cross-sectional moment of inertia, that's really what distinguishes these two beams, is how they're presented to the load. So when we look at this and we say beam A and beam B, which one's going to have the greater resistance in bending? And that means that if the force is equal, which will deform less? So it's identical beams, identical force. The only difference is orientation. Beam A is in joist, beam B is in plank. So when we look at this, you can see that beam B, the one that is in plank, deforms quite a bit more. So what you're looking at is basically a deformation graph. It's a little cartoonish, so it's amplified, and the red shows the amount of deformation, with red being the most and blue being the least. And you'll see that the beam A in joist format hardly deforms at all. Beam B in plank deforms quite a bit. So why? And the answer to that is because the way the load is presented to the molecules within the beam. So when I look at a beam and I look at defining it, I have to define it as a height and a base. And the height is always the length that is in line with the force. So my force was coming down from the top of the screen, and in this instance, the height is that dimension opposing the force or going vertically. Now these two beams have a difference in the moment of inertia because of the way they were oriented. So beam A, you'll remember, was stood up, so the height was pretty tall relative to the rest of the beam. So let's look at how we calculate the moment of inertia of a rectangle. And the formula is really pretty straightforward. It's basically the base times the height cubed divided by 12. And you can see right away, as long as we're all dimensionally consistent, in other words, the base and the height are measured in the same dimension, I end up with that linear dimension to the fourth power. In this instance, we were given inches. So we look at the two moments of inertia. If I look at beam A, 5.5 inches tall, 1.5 inches wide, I end up doing the math, and I boil it down to, I have a moment of inertia of 21 inches to the fourth power. Now it's kind of important to remember that we're looking at the height to the third power. And because we're looking at that, minor variations in the height make major variations in the moment of inertia. So let's see an example of that. Here's beam B. Again, beam B is in plank orientation, and now my height is measured at 1.5 inches, and my base is 5.5 inches. Same beam. So when I do the math and multiply this out, what I end up with is 1.5 inches to the fourth power. Quite a dramatic difference. So remember, beam A had 21 inches to the fourth power. Beam B had 1.5 inches to the fourth power. This makes beam A and beam B different in their relative rigidities, or beam A is 14 times stiffer than beam B. That's just from orientation. When we look at shapes, and we learned a little bit about the centroid, the question here is, why do we have compound shapes used in a structural design? And think about the way that the loads are in a building. So an example, an I-beam that's in the roof of our building that we can see as we look up, there's definitely a load coming straight down from the weight of the roof supporting. But why do we want to have a moment of inertia left and right by the I part of the beam? There's a lot of reasons. There's reasons that we want an I-beam, the flange is what that's called, to attach things to. Also because we don't have forces in just one direction. We have forces in many directions. We have wind loads, seismic loads, all sorts of different loads that we have to counter using different orientations of the I-beam. But the predominant force is down. So let's look at a composite versus a non-composite beam. And when I say non-composite, just a basic rectangle versus a composite beam. So here we have a beam, and basically what it is 4 by 2.5. If you're quick with your math, you'll see that that's 10 square inches. Well, if I take that 10 square inches and I rearrange that into an I-beam format, and you can do the math, but trust me, the I-beam in the middle of your screen is 10 square inches in area. I've used the same amount of material. I can also about double the material, a little over double, 2.4 times the material, and make a tall 9.5 by 2.5 inch beam. But what you're going to see is, if I look at the moment of inertia of the rectangle, it's 13.3 inches to the fourth power. If I apply my moment of inertia to a composite force, and that's a little bit beyond the scope of what I'm going to teach you in this class, but if I do that, I actually would get 130 inches to the fourth power. So I got about 10 times the stiffness with the same amount of material as the basic rectangle. Now, if I made a bigger rectangle, I do get more stiffness. I get 178 inches to the fourth power. But holy smokes, I used 2.5 times, well, 2.38 times the amount of material. So what you're seeing is, if I go to a composite shape like an I-beam, I get some advantages like a flange, three-dimensional loading capacity, and I also get very, very much higher moment of inertia for the same amount of material. That's why we use I-beams. So the other thing we got to talk about when we're talking about how stiff some object is or a beam is what is it made of? And the comparison here is bubblegum to steel. We know that bubblegum is much more flexible and bends easier than steel does. And we represent that with a modulus of elasticity. And that basically is the ratio of stress to strain in an object, which we'll learn about here in a little while when we look at some more material science. We sometimes talk about that as coefficient of elasticity, elasticity modulus, Young's modulus, a lot of different terms for the same idea, and that is how stiff is the material. Not the shape, but the material. So now I take two objects that are the same shape, and I compare their modulus of elasticity. And in general, the higher the number for the modulus of elasticity, the greater the resistance to deformation. Now, these numbers for modulus of elasticity get really, really large. It is not at all uncommon. Example like Douglas fir is somewhere in the order of 1.51 million pounds per square inch. So a significant high number. It's not uncommon to see a very high number in the modulus of elasticity. So let's look at these two. I've got two beams here, A and B. One is Douglas fir, wood. The other is ABS plastic. Exactly the same dimensions, exactly the same moment of inertia. So the geometry provides the same stiffness, but the material is different. So really the only thing that distinguishes these two is the material. So what do you think will have more rigidity, A or B? The wood or the plastic with an identical load. So my load again is coming down vertically onto the beam. And here you see the deformation modeled. And you'll see that the plastic beam deforms quite a bit more than the wooden beam does. Now, that comparison is how we can describe the modulus of elasticity. Or the beam that's made out of wood has a much higher modulus of elasticity. It deflects less. So we look at why this is. It's the difference in the modulus of elasticity, and it's the ability of the material to deform and return to its original shape. Now, it's important for you to understand that the modulus of elasticity applies over the region, the linear region of the beam. So if I take any object and I bend it past where it springs back, I've entered into plastic deformation or destruction in some cases. So this is only in the linear region of the material. So I can predict how much a beam is going to deflect by a few different terms. I can talk about the force that's applied to it, its orientation or the geometry, which we represent by the moment of inertia, and then the material, which is represented by the modulus of elasticity. So when we talk about this, it's called delta max. What is the maximum amount of deflection that a beam will undergo? So we've got a formula for this, and really what it depends upon is the length of the span, the modulus of elasticity, the moment of inertia, and then how much load is put on the beam. So let's look at that formula. You'll find this on your formula sheet. And very simply stated, it just says that delta max is equal to the force times the length between supports cubed divided by 48, and then the moment of inertia and the modulus of elasticity. That's what that formula is saying. Now, you're going to notice something right away. L is cubed. So again, minor changes in the length between supports make for major deformation differences. The other important thing to understand is this is only for a point load at the middle of the beam. There's different formulas for the load being distributed in different places, but this load is in the middle of the beam. So let's look at this a little bit more in depth. So if I look at a beam deflection, and here I've got beam A, and this is 1.8 million psi. I don't know what kind of wood it's made out of. It's some kind of wood, though. And I've got a 250-pound force First important thing to understand is this length right here, the span, this needs to be in the same units as my moment of inertia, I. So if I is given to me in inches, and in this instance, inches to the fourth power, but L is given to me in feet, I need to get my length into the same units as my moment of inertia. So let's go through and do some math on it. It's a pretty simple equation. So the delta max of that beam is going to be 250 pounds of force times 96 inches to the third power, divided by 48, and then the modulus of elasticity, and divided by the moment of inertia. If you went through and canceled your units, what you would see, PSI is pounds per square inch, you'd see that you come out in inches as your units. Now if I look at beam B, all that's changed here is my E is 419,000 pounds per square inch. So E changed. And I multiply this out, get the same 250 pounds force, the same span of 96 inches, and then my changed E value of 419,000 divided by the same moment of inertia. I get 0.53 inches. So that is why I have a larger deflection calculation. And there you see the delta max is 0.12 versus 0.53. Now this was a linear relationship. In other words, my E for beam B is 419,000. My E for beam A is 1.8 million, a little over 4 times as much. Notice my deflection is 0.12 and 0.53, a little over 4 times more deflection. So a linear relationship between the material difference, modulus of elasticity, and the amount of deflection. You'll see from this formula that if E goes up, deflection goes down. If I goes up, deflection goes down. If L goes up, deflection goes way up. And that's why we don't see a lot of cantilevered extreme lengths, because of the deflection. So there you have the ratio of deflections represented by the ratio of the modulus of elasticities as well. Pretty straightforward as we work through this lab. There's that deflection shown with the plastic on top and the wood on the bottom. So that's it for the idea of beam deflection and modulus of elasticity. Remember that modulus of elasticity represents the relative stiffness of the material. Moment of inertia, and that's cross-sectional moment of inertia, measured in our examples will be inches to the fourth power. That is the relative stiffness due to the geometry. So a bigger number means more stiff. And delta max is the deflection of the beam. That's it. Thanks for